In this video, we're going to talk about the activation of oxygen by HEME. The primary function of HEME is to take molecular oxygen, O2, and essentially convert it to an oxygen HEME species that can be used to insert that oxygen into a substrate, another molecule. Okay. Initially, HEME is in a kind of a planar. See this nitrogen here, 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 and here, they're all in the same plane. It's like a parallelogram, but it's a planar low spin state. When we say low spin, we mean there's a minimal number of unpaired electrons. Okay. Initially, the HEME is attached to cysteine 237 on the enzyme, on the P450 enzyme, and there's a water molecule that's coordinated to the top of the iron. Okay. What happens next is the substrate that comes in, we're just going to model it as like some RH organic molecule. It forces the water out of that its binding site on top, and when that happens, we end up creating a 5 coordinate with our sulfur here on the bottom, still connected to the enzyme. Okay, but now our substrate is sitting above the HEME, and the HEME has converted to a 5 coordinate. So sulfur, nitrogen, 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 nitrogen. So it's 5 coordinate. This is a high spin compound now. That means that there are more unpaired electrons typically in it. This step here, in which the water is displaced, changes the reduction potential of the iron significantly. So, for example, over here, initially the reduction potential is minus 330 millivolts, and once the water is displaced, the reduction potential becomes minus 173 millivolts. Okay, an increase in reductive potential like this essentially means that this iron species is more likely to acquire electrons. Okay. So the first electron then is transferred to the HEME by FMNH. Okay, FMNH loses an electron, and I show that here by just having 1 electron on it. Obviously they're paired here, so you could kind of draw it like this, and then there's 1 electron here. But in this transfer, electron transfer here, what happens is the iron becomes iron 2, ferrous HEME. Okay. Now this ferrous HEME reacts with molecular oxygen to form the first oxygen HEME species, this species here. Now this species is further reduced. It picks up another electron from FMN. Again, I'm showing that by this little radical electron here. And that electron, you'll notice here that there are only 1, 2, 3, 4, 5 electrons right there, right? So during this electron transfer, the next electron ends up right here like that. That gives this dioxo species a negative charge, okay, on this outer oxygen here. On an adjacent enzyme, amino acid, there's a little acidic residue, and that protonates this oxygen. I'm showing that here with the red electron movements. Okay, so that protonates it, and we make the peroxo HEME intermediate. And then what happens is, again, another acidic residue, okay, reacts with this peroxo intermediate and forms this final oxoferryl HEME species. You can draw a number of different resonance structures for this. If I could remove an electron from the iron and push it up onto the oxygen, and that would make it iron 4, okay, and we'd have 1 unpaired electron up there. Some folks have even gone as far to draw this resonance structure, in which you just kind of pull the electron out. We don't know exactly where it is, but we say that this is still iron 4, but it has a plus radical kind of qualifier on it here to indicate that it's the same. All these species have the same number of electrons. They're all resonance structures, so all these species are all the same. Okay, but ultimately, it's one of these species that is believed to be the reactive intermediate. In most of the reactions or the reactive heme intermediate. Most of the reactions we'll look at from here on out, I'm going to start with this oxoferroheme intermediate here, and then we'll see how that reacts with various substrates to form oxygenated compounds.